Hi students! Okay, so we are on the fifth chapter in our Psych 218, Analysis of Behavioral Data. And so after four chapters of looking at statistical procedures, frequency distributions, central tendencies, that is expected values, and variability, that is spread, now we're going to start comparing not just scores with each other or specifically a score with the mean, but now we're going to want to start comparing distributions. Now, this could be one population to another population distribution, or it could be a sample distribution with another sample distribution, or it could be a sample distribution with a population distribution. And so this chapter covers how we're going to do this, and we're going to use something called z-scores. And a z-score specifically, as the title says, is a location score. And it is a standardized location score. And when you got a whole bunch of z-scores together, you're going to make a standardized distribution. So when you have x-scores, that is your raw scores, you're going to get a distribution of x's. So let's say, for example, I have x, and if you put a whole bunch of x's together, x2, x3, and so on, and you put them in a distribution like this, obviously there are going to be more x's than this if we pretend it's a population distribution, with a mu of something. Again, this could be like body temperature, GPA, height, anything at all, as long as it's some distribution that is normally distributed, where most of the scores are going to pile up in the middle, and it's going to be symmetrical. So you're going to have roughly the same number of people who score higher than average, and roughly the same number of people who score lower than average. So two things are going to be key here for our z-score. We're going to need the mean of a distribution, and we're going to need to know the standard deviation of the distribution. And with those things, we're going to get a score that's going to be z, that is a location score, specifically the number of standard deviations any given score in that distribution is away from the mean. And so instead of x's in there, you're going to put z's. Again, there would be more, but I'm just going to draw a few for simplicity's sake. And when we are able to transform any distribution, here we're going to say any normal distribution, be it sample or population. In this case, we'll work mostly with population distribution because you're going to see mu and sigma. These are parameter values a lot more. Once we change these distributions into a distribution of z-scores, and we do this for any population distribution, then we can start comparing distributions, not just comparing scores. And here's an example of this. Here is a table of 6 different English language proficiency tests that UBC has for their English language admission requirements. I did this with our classes, whether they're online or in the classroom, as a way to help us picture and think about how we might need to compare distributions. So the goal here for international students who go through this system would be, I need to show UBC that I pass the English language admissions requirements in order to study at UBC. So one of these 6 tests must be taken, and one of the requirements must be met in order for UBC to go, oh yeah, you pass at least that requirement. Let's look at the others. And if you get in, hey, congratulations. And this is one of the more practical applications of this, because you probably as a college student want to transfer to university. Maybe they have programs that you want there, for example. But look at these 6 tests though. Not only do they have different names, and you may have heard different things about them, and yes, I'm aware that most of the listeners here might have taken IELTS, particularly Canadian international students, but these 6 tests are available because students can come from various places in the world, and Look though, not just the names are different, and not just the tests are different, but their scores are different too. So if you were to compare the scores, these are minimum scores to get in, by the way, they're all different, aren't they? You got 70 for one test, 180 for another, 600 for another, and, 90 for the different bands in TOEFL, and IELTS has its own bands and system. So if you just said, oh, I got a 6.5 in something, yeah, you can probably guess it's IELTS, but how does that compare with the other tests? You may think for a student, oh, okay, from a student's perspective, well, which test is easier to get that minimum score? From an institution's perspective, they might think, oh, which test is more reliable? As in, like, hey, if a student meets the minimum score of a particular test, this should predict how well they're going to do in, writing classes especially. So it is important for us to compare, not just for students comparing between how easy or how, hard a test is for their requirements, but also for, teachers and institutions to compare, like, let's say, tests to see how reliable they are. And you might be thinking something already with the tests that you do. Well, maybe if we convert all these scores into some kind of percentage between, I don't know, 0 to 100. And that is a very common and a very useful way for, changing any test score into a proportion. So then, for example, oh, if, let's say, a test is out of 100 and you got 50, well, that's pretty easy. It's 50%. Let's say if it was 50, but the test was out of 70, well, then that's 5 over 7. That's more than 50%. And so for individual scores, proportions are good. And we've, encountered proportions before when we use frequency distributions, and we covered that. Proportions will also be useful for probability as we look at parts of a distribution that, a score is placed in that distribution. And we'll talk more about that in chapter 6. This is the next chapter. But what if you want to not just compare, individual scores, but also distributions of scores? Remember how we talked about the range and you only compare between the maximum and minimum? And we use the standard deviation with the mean as a reference point, so then we can, compare each score with a central score or a measure of central tendency, in this case the mean, and you can compare the values. In this case, just like we need a standard deviation to let us see how the scores in a distribution are spread out, its variability, we can use standard deviations to compare distributions by measuring each score in the number of standard deviations. So instead of percentages, we're going to measure the scores in Zs. And Z, for now, we're going to call it a location score, because we're measuring each score by the number of standard deviations away from the mean. And so the standard deviation score is a distance score. And when we know the distance, it's away from the mean, and the mean is 0, then anything less than or greater than 0, we know it's some distance away from the mean in standard deviations. And that's the essence of Z-scores. Once you know that we need to compare distributions and not just individual scores, and we need some way for all the scores in any distribution to make them consistent for any distribution, for us to describe any score in something other than its raw value, not just X's, but Z's, then we can start comparing distributions. So in the slides coming up, we'll provide pictures of this. We'll provide techniques to help you practice this. So again, we're going to learn how we can use Z-scores to compare distributions. So there are 5 learning outcomes that we need to do to cover this topic. So first, we need to be able to describe how a Z-score is a location score in the distribution. And so once you memorize and recite and apply, the definition of a z-score, that is the number of standard deviations a raw score is away from the mean, then you're able to transform x-scores into z-scores, and you're able to transform the z-score back into an x value. So that's going to be your first 3 learning outcomes. And after you've done enough practice with changing x values into z-scores, and you'll see the effects of standardizing a distribution. And some of these things we already talked about. If in a normal distribution, again, we've covered what that is, where all the scores are going to pile up in, well, most, I would never use the word all here, most of the scores are going to pile up near the mean or on the mean. And the mean itself would be the central tendency here. And so if a score happens to have the value of the mean, the x value is the mean, then it's no distance away from the mean, and the z-score would be 0. And then, again, remember, any score away from the mean would have a positive or negative value. You'll see what happens to those values once you transform the x's into z's. And you'll see that the first thing is the mean for a distribution of raw scores is going to have some number. But the mean for the distribution of z-scores is always going to be 0. So we're going to describe stuff like this. And finally, the last step, and this happens quite a lot for standardized tests, including tests like SATs, Scholastic Aptitude Tests, GRE, Graduate Records Examination, LSAT, GMAT, other standardized tests that you may see. How they do it is they get the scores from their tests, and then they would transform them into z-scores and then assign a value to that mean. So it's going to be something like 100, it could be 300 or something else. And so the scores are then standardized to make its own standardized distribution. And the scores are transformed then. So it will no longer read like 0. And imagine if you get average on a test, on a standardized test, and you're told, oh, you got a 0. So either it sounds like a game of golf, or it might sound not very pleasant to you because, oh, you did all this work and you got 0. So another way of looking at it is, for example, instead of calling the mean 0, it could be 100, let's say, especially if, the test was out of 200 per se, and the average score happens to be 100. And so standardizing a distribution and transforming scores to a standardized distribution helps the test takers and the people comparing these distributions to go, okay, yeah, I know what the mean is, but it's going to be something that's easier to read and perhaps easier to accept too. So these are used for standardized tests. The math tools you'll need for this, 2 obvious things you're going to need: the mean and the standard deviation. These 2 values are going to be your foundations for calculating your z-score. And there's one more thing that you're going to need, and see if you can think what it is. If you're thinking, oh, I need the raw score too, you're right. Well, again, the definition, as we've said a few times, is, well, a z-score is the number of standard deviations, which has the words in it, 1. A raw score is away from the mean. Again, it's a location score. If you only have the mean and standard deviation and you don't have the score you're looking at, you can't get a z-score, unless that score happens to be the mean, but you haven't asked for it. So you need 3 things: the mean, the standard deviation, the raw score, which you're probably given most of the time or you'll be asked to calculate it, and you're going to need a tool of basic algebra to calculate z-scores or transform the z-scores back into x values. So this slide then covers the purpose of z-scores. In these points, you'll see that, okay, the first point, we want to identify and describe the location of every score in the distribution. So in the last chapter, we have found variability in terms of standard deviation. And we derived that from first getting the mean, which is what was in chapter 3. And then we calculate the sum of squares, because we can't just add all the deviation scores together because that's going to zero out. because the negative deviation scores are going to cancel out the positive deviation scores. Once you get your sum of squares, you get your variance. Again, you want to be careful. When you calculate variance, you want to use the right denominator, n, big N for population, n minus 1, which is degrees of freedom for sample. And then you get standard deviation from that after square rooting the variance. But then you only do that for one distribution. And it doesn't really talk about the scores at all. Here in chapter 5, when we look at z-scores, now we're going to get every score in the distribution and find some way to describe its location in the distribution. And we measure them in standard deviations. And the word standard is going to make a connection for you, because once we do this, we'll be able to standardize an entire distribution. So instead of, a distribution of x's with a mean, of some value in the middle, we're going to transform these scores into z-scores, where a score with the value of the mean is going to be 0 distances or 0 standard deviations away from the mean, and then we start measuring scores as standard deviations away from the mean. And then in this distribution, you'll get z's instead of x's. Now, one thing I'll say right off the bat is that the distribution shape doesn't change. The location of the scores don't change. Each score stays where it is. But instead of measuring each score by its raw value, that is like what we tested the participants with and record the score, we transform each score in standard deviations. And so, as the third point said, we can take different distributions once we transform them into location scores, and then this way we can compare each distribution. So, for example, here's another distribution. I'm going to call this B and call this A. Yes, even though they're x's and mu's, but let's say for one test the average was 60%, or 60 out of 100. And the other test was, I don't know, harder, and it was 50%. And so the x's in each distribution are, their own scores. And if you want to compare them, what you can do is maybe look at the distributions and talk about it in terms of central tendency. You go like, oh yeah, the means are different. One test seems to be easier than the other one. Or you can talk about, its variability. Oh, one test seems to have a larger spread, perhaps. Distribution B seems to have a wider, curve. But beyond that, there isn't much you can do. However, if you take the same distributions, and I'm going to just do mirror image here because this B over here looks the same shape as the B on the right. And then I'll draw a thinner distribution. Now, if we transform these distributions into z-scores, it's -1, this is 1. Notice now, because we're labeling each score, we're identifying and defining them and describing them as location scores. The raw scores are no longer there. We don't see them. But the locations are the same, and now we're able to say with each score where they are in relation to something that is consistent, the mean, for each distribution. And so when we compare z-scores, for example, something that has a z of 0 versus something that has a z of, let's say, +3, right away. For any distribution, something with a z of 3, for example, it's 3 standard deviations away from the mean, above the mean, and oh wow, that person did really well or scored really high. Whereas somebody that got -1 standard deviations below the mean, then you go, okay, that person scored below the mean. So we can start describing distributions and scores in the distribution like that instead of raw values. And that's what the z does. So here's an example of this. And with these examples, you can practice calculating z-scores almost immediately. So notice here there's a mean. And another tip here, once you look at tables and you see symbols, if you see Greek letters, for example, the standard deviation is sigma, you know you're working with population distributions. In this case, you're working with parameters. And for z-scores, you are most likely going to be working with parameters anyway, because you're working with population mean and standard deviation from the population. So here, again, remember the z-score is, the number of standard deviations away from the mean. In this case, if we know the standard deviation for this particular distribution, distribution A right now is 3x points, then a score of 73 in that distribution is going to be 1 standard deviation away from the mean. So if there was an axis here, and this axis is going to be z-scores, and you'll see this in another slide. A score of 70 in distribution A would have 0 standard deviations away from the mean, so the z would be 0. And, a score of 73 would be 1 standard deviation away from the mean, or above the mean in this case, because it's already been given that in this distribution, sigma standard deviation for this distribution is 3. So likewise, you can go, oh, well, if it was 1 standard deviation below the mean, what x value would that be? Well, I take the standard deviation of 3, subtract it from 70, and if you're thinking 67, you'll be absolutely right. So that would be -1 standard deviation away, below the mean. 76 here, then, you can take a moment and see and determine how many standard deviations is the x value of 76 away from the mean of 70. If you're thinking 2 standard deviations above the mean, plus 2 for z, you're right. And one more test. Well, what if you're looking for a z-score of -2? That is 2 standard deviations below the mean. In that case, then, 1 standard deviation is going to be 3x points. Okay? And so 70 minus 2 times 3, or 70 minus 6, well, that's going to be 64. And so, very quickly, as long as you know, or you're given the population mean, in this case it's the mu, and you're given the population standard deviation, this case it's the sigma, and you're given some raw value to work with, you'll be able to calculate z-scores right away. And the process is pretty simple. So here's another one. Notice then, in comparison to distribution A, you got the same x value here at 76. You have the same population mean, which is 70. There is one change in distribution B that is different from distribution A, though. And take a moment and see if you can figure out what the difference is. If you see that distribution B has a sigma of 12, which is not the same as distribution A with a sigma of 3, that is, the standard deviation is a lot larger in B. Again, the pictures are not to scale, so we must work with the numbers here. In your practice questions and your tests, work with the data, the numbers. That's going to be the ones that will help you in your calculation, not the pictures themselves necessarily. And often when I say look at the picture, what we mean is look at the numbers. And if you have drawn the distributions to scale, be they distribution or frequency distribution polygons or curves, or later on scatter plots in when we do correlation, if they're drawn to scale, then yeah, you can look at the pictures also, but the numbers are first. Anyway, because the standard deviation is a lot larger this time, the same x value of 76 no longer has the same z-score, because if in distribution B, and we're talking about distribution B here, where 1 standard deviation is no longer 3 x points, but 12 x points, then an x value of 76, and if we do another z-axis here, again, the mean would have a z value of 0. One standard deviation away would be 82 because we have established in distribution B that the sigma standard deviation for that distribution is 12. And so 76, again, well, we're 6 points away from the mean. And if one standard deviation is 12 points, what would the number be? If you're thinking 0.5 above the mean, you're right. So you can see here, a z-score is determined by the population mean and the population standard deviation. So yes, you can have two of the same parts out of three. So you can have the same population mean and you can look at the same raw score. But if the distribution has a different standard deviation, the location is going to be different. So a question for you. Which one of these distribution has the x value of 76 closer to the mean of 70? If you're thinking distribution B, where the standard deviation is 12, you're right. And so what we're measuring here then is how far a score is away from the mean. It could be above or below. And we measure that in the number of standard deviations. Again, now at this point, we have visually and mathematically shown you the essence of the z-score. And so those are the points that you see here in word form. Again, the z describes the exact location of a distribution, as we have talked about in the previous slide and also the next slide. And so the sign then tells us in a z-score whether the value is above or below the mean. And the number of the z-score always tells us this, and this is kind of the definition of a z-score. It's the distance between the score and the mean in standard deviations. So you can paraphrase this in a way that works for you, but remember, you must include the three parts. You need to include the score and the mean and describe them as a relationship between them, specifically the distance between a score and the mean, and you're measuring that in standard deviations or standard deviation units. The formula is derived from this definition. Just like there's a definitional formula for sum of squares, from which you can see the definitional formula is derived from its definition, right? So you square all the deviation scores first. That is the distance between a score and a mean. You have to square those first and then add them. So again, knowing the definition and applying it and being able to paraphrase it in your own words will help you use the formula correctly every time. Just trying to memorize the formula alone, especially if you're dealing with a different question or you're dealing with a different distribution, be it sample or population or something else, if you just know the formula, it will mess you up. So here then is a distribution of z-scores. And here you might notice the thing we just talked about in picture form. Again, the raw values would have a mu, population mean, it could be any number, and then sigma, which would be the standard deviation. The standard deviation stays the same because we're measuring z-scores and standard deviations. But once we started changing the x values into z's, the mean would have a z-score of 0 because it's no distance away from the mean. It's where the mean is. And then any value above or below the mean would have signs. So a value above the mean would have a positive z-score. And if it's +1, it's 1 standard deviation away. If a value is -2, that means it's 2 standard deviations below the mean. And as you can see here, when we measure scores and standard deviations for a normal distribution, you can start to see, you would start noticing patterns like, oh, well, the score's in the middle, and that's the mode and median too. And then most of the scores would end up, between plus and -1. And then you see even more scores between plus and -2, and then there is a +3 somewhere here and a -3 somewhere here. So now for any distribution, you can say with certainty and clarity that if you say, if somebody has a z-score of, let's say, 0, well, you know exactly, so they exactly scored on average. But if you tell them, oh, somebody scored a plus or minus something big, it could be +2 or +3, then you know, okay, that person has gotten very extreme high or low score. And the Z-score tells you that immediately if you apply the concept. So here's some learning checks for you. Number 1. A Z-score of +1 indicates a position in the distribution. So pick your choice here. A, B, C, or D. I'll let you read those out loud and figure out an answer there. You can pause the video at this point to read and figure out your answer. Remember the definition of a Z-score. Remember how we got that definition. If you picked B, a Z-score of +1 means, oh, it's above the mean because it's plus, and it's 1 standard deviation above the mean because, well, it's 1. That's what Z measures. Then you're good. 1 point here would mean an X value, so those are not correct. And anything with below, that's definitely not correct either because the positive sign here means above the mean. Let's try true and false questions. Then, okay, for A, a negative Z-score indicates a location below the mean. True or false? And B, a score close to the mean has a Z-score close to 1. So take a moment to figure out these two. You can pause at this point. For A, again, a negative Z-score, yeah, it does mean the score is below the mean. And you can review that in this slide. And you can also review the next true-false question in the same slide too, because, again, if a score is close to the mean, it's going to be close to 0 because, well, the mean is no standard deviations away from the mean. And when I say no standard deviations, that's 0. If when you watch these video lectures and you find, oh, okay, this stuff seems repetitive, good. And if you're thinking in terms of, oh, it's repetitive because I understand it, great. There are lots of practice questions you can do, and it's a good feeling to have because that means you're ready for practice. If you're watching this and you still don't, if you get it as you gradually go on, that's great too. Again, feel free to pause during after these learning checks and take breaks, review the parts, practice writing definitions or practice the questions you see on the slide. Or if you're struggling, then take a break, come back and try again, or email us directly if you have further questions. Again, remember the textbook is the key. They'll give you resources along with our web tutorials to give you practice questions. So then here's the next part. If you look at this equation and you understand how it works and you can translate it into plain English, great. You're already understanding the essence of the Z-score and you can calculate them pretty well. And you should be able to change X values into Z and Z values into X's back and forth and standardize the distributions too. But anyway, here's the equation. I can also write it this way. So yeah, it's the deviation score divided by the number of standard deviations. So that's what the points say. You need the distance between the score and the mean. That's the numerator. You need the standard deviation. That's your denominator, the bottom bit of the fraction. And the Z-score, again, by definition, indicates the number of standard deviations a score is away from the mean. A positive Z value would be above the mean, and a negative Z value would be below the mean. Again, this is not a percentage, it's a location in number of standard deviations a score is away from the mean, above or below. So you can do also quote-unquote the opposite, where instead of getting a Z-score, you want an X value. So let's say, if somebody told you, that person got an A, and as we talked about this in a few recordings and classes, if you're taking the classes with me, letter grades are in one sense or another standard deviations away from the mean if C was average, right? So B would be 1 standard deviation in the distribution away from the mean, and A would be 2 standard deviations away from the mean. Of course, if you get an A plus, you're close to 3 standard deviations, you get a really high score, and F is anything lower than 50%. Having said that, if you got an A and you know what the average is, you can, for example, estimate, assuming you know somehow the population standard deviation, you can go, oh yeah, I think I know what the person got. You can either guess that or calculate that. But again, we're using the same formula, and we're using algebra to figure out, oh, okay, well, I know the Z, I know the mean, I know the standard deviation. Well, I can calculate the X. Well, the X, again, is a score away from the mean, right? And so if we know the mean, and we know the standard deviation, the Z tells us its location. If it's a positive value, then you would expect that X would be above the mean. And then the standard deviation, your sigma, would be the multiplier. If a Z score is negative, then you'd expect the score to be less than the mean or below the mean. And the standard deviation then is the multiplier. So that's what our points say. With the Z-score formula, you can solve for X using algebra. In the slide here, it says algebraically. And the Z-score here is the multiplier. And it can be positive or negative, which indicates the direction of the X. And the direction also tells us where the X is in relation to the mean. So here's an example of this. Take a moment and see what Z-score you would give for 59 in this distribution. First, you might want to figure out what the mean is, and we know that's 65. And you might want to figure out what one standard deviation is. If you're given clues like, oh, okay, I know 59 is 6 points away from 65 is actually 6 points below 65, and in the picture we're given a clue, okay, that's 2 standard deviations away, and if 2 standard deviations is worth 6 points, then 1 standard deviation is worth 3 points. And so you can calculate the Z-score for 59 as, well, 2 standard deviations away, and you can use the formula if you needed to, x minus mu over sigma. So, okay, well, 59 minus 65, and you can tell already is going to be a negative number because it's below the mean, or you just calculate 59 minus 65. A smaller number subtracted by a larger number is going to be negative no matter what. And then, oh, okay, I figured out the standard deviation is 3, so it's negative 6 over 3, which is negative 2. In a Z-score, the sign is important here. So, if this was a Z value, 0, this would be negative 2. And here would be negative 1. And take a moment and see if you can figure out what a Z-score of negative 1 is. Well, we can do this too. So again, we have the, oh, no, not the X. We're solving for X. So here we got that one. Let's find our X here. Okay, again, I need my multiplier. And so, okay, well, I got mu, which is 65, plus negative 1, that's our Z, and the standard deviation is 1, so, well, okay, 65 plus negative 3, I'm going to do all the steps, just like I would require the students in my class to do when they're showing the work. Well, 65 minus 3, well, that's 62. So again, here's a simple visual representation of a Z-score from which you can do both things. You can calculate the Z-score, and you can also calculate an X-score. For the math part, we say using the formula. For the definition part, we say, well, we measure scores in standard deviations. So here's the next learning check then. For a population of with mu equals 50 and a standard deviation of 10, what is the X value that corresponds to a Z-score of 0.4? Take a moment and calculate your answer there. Again, with these simple questions, you don't necessarily need the formula per se, but it's good to practice writing it out too. And you probably don't need a calculator for this. But if you do, well, you do what you have to do, but you want to move away from the calculator for stuff like this for now, especially in the first 5 to 6 chapters. So if you answered 54, you're right. Well, first of all, the Z value is positive, so again, you would expect a value above the mean, so B and D are out of the question. Next, you think, oh, okay, it's a Z score. It's not by points, so you could eliminate A right there if you wanted to. But remember, the technical way of doing it and what you're supposed to do by definition is go, oh, I know the standard deviation is 10 points above the mean. One standard deviation is 60. So if a Z score is 0.4, well, that's 4/10. And so if this is nice, standard deviation is 10 points, well, that's 4 out of 10 points. So it's 4 plus 50, which is 54. Okay, next 2 questions, true, false. These might get a little confusing, but again, read the question carefully and work out the components. A, if the mu is 40 in a given distribution and x is 50, and that corresponds to a Z score of plus 2, then what is sigma? Does sigma equal 10 points? True or false? And for the next question, if sigma is 20 in a given distribution, a score above the mean by 10 points would have a Z score of 1. True or false? For A, in that distribution where mu is 40 and 50 corresponds to a Z score of 2, then no, sigma isn't 10. That's not one standard deviation, because 50 here corresponds to 2 standard deviations away from the mean. So here in this case then, 50 here would be 2 standard deviations away from the mean, and the distance between 50 and 40 is 10. So a difference of 10 here means 2 standard deviations. So if that's the case, then sigma isn't 10. Sigma would be 5, where 2 standard deviations would be a difference of 10 points, not 20, if sigma was indeed 10. Again, you can practice this too. If sigma was indeed 10 and the Z score was 2, what would be the X value? It would not be 50, but it would be 60. So again, lots of opportunities to practice there once you got your components down. For B, if sigma is 20, then no. A Z score of 1 would not say that a score is above the mean by 10 points. A Z score of 1 means 1 standard deviation away, and that would mean 20 points above the mean. When this standard deviation is 20, a score of 10 above the mean would actually have a Z score of 0.5 because it is half a standard deviation away from the mean. 10 is half of 20. So the next step then in our chapter is to standardize a distribution. So once we're able to transform at least one score or one X value into a Z score, we should be able to, repeat this process and transform every X value into a Z score. Only then can we compare distributions. So that's what the points in this slide are about. We need to be able to transform every X value into a Z score, every. And so then, once we complete this transformation for distribution, we start to notice some things. The scores will be Z scores, but they have the same shape as the original distribution. We haven't moved the values, we just transformed them, we just multiplied them by something, and we measured them by standard deviations. Okay? And the first big change you notice is that the mean of the Z score distribution, your standardized distribution, or your standard distribution, specifically standard normal distribution, will have a mean of 0 all the time. And one standard deviation in this distribution is always going to be 1. And it cannot be any other number because we're measuring in the number of standard deviations. And by doing this for all the distributions, then we can start comparing them. Otherwise, we're just comparing x's, which is in an idiom, comparing apples and oranges, which won't work very well. So again, this is an example of transforming x's into z's. As you can see, the mu transforms into 0, and the standard deviation scores then are just what they are. One standard deviation above is +1, one standard deviation below is -1, and all of these scores then, the x values would be transformed into z scores, and you get a distribution of z's with a standard deviation of 1 and a mean of 0 all the time. That's a z distribution. Okay. So here's another picture showing you kind of the before and after if you're transforming x's into z's. Here you see the mu is 100 and the standard deviation is 10. Because we're transforming all the scores in the distribution, I'm going to shade all this. And these are x's, x1, x2, x3, and so on. Now you're transforming these into z1, z2, z3, etc. And so the mu for this z-score distribution would have a mu of 0 and a standard deviation of 1. Once you transform the distributions you're looking at, or the populations, most likely in this case, then you're able to compare distributions as z distributions. Because you're measuring everything by standard deviation scores, or in this case, z-scores. So one of the things you're going to do if you're going to draw this out in your own practices is you're going to relabel the axes. You're going to change from the x-axis, well, from labeling the x-axis with x scores, you're going to label them with z scores. The mean of x value becomes 0, standard deviations away from the mean, which is the z-score. Every standard deviation then would have a +1 or -1 integer, depending on whether it's above or below the mean. So here you can tell in the original distribution of x scores, 110 is going to be 1 standard deviation away from the mean. So here's a little practice for you. In the original distribution, how much is 1 standard deviation? If you're thinking, oh, I know this, we're just looking at it. Sigma in the original distribution of x values is going to be 10. So 2 standard deviations above the mean would be 120, and that would be a z-score of 2. And there'll be 2 standard deviations because it is 20 points above the mean. And you can do the same with the -2. So let's say on the negative side, a score of 90 would be -1, or 1 standard deviation away below the mean. Notice in this slide, yet another graphic here. Again, this is a very important concept because now we're going to teach you in the rest of this course how we can start comparing distributions. And without standardizing a distribution, there's no way for us to do any of this. We cannot do inferential statistics. We cannot make inferences. We cannot make comparisons unless we have a consistent way of comparing distributions. So again, these pictures are why we're having these, and we're having more than one picture to show you how we're changing any distribution into a standard distribution or standardized distribution. Notice here, again, the shape doesn't change. All the blocks are the same. Well, if I were to do the blocks again, 1, 2, 3, 4, 5, 6, again, it's the same shape. The scores don't move. We are relabeling the scores. So the shape is exactly the same, but we're measuring the scores by standard deviations. So the values on the x-axis change. In distribution A, they're x values, so we use x values on the x-axis. On distribution B, it's a standardized distribution because we're using z-scores, and the x-axis now has labels of z-scores. The frequency on the y-axis don't change. So it's still counting the people. we don't change that. So the shape doesn't change either. Okay. So this is the slide where we start talking about using z-scores for comparisons. Because you can measure any distribution by z-scores, that is, you can measure, oh, okay, there's a mean and there's a standard deviation, assuming you're measuring more than one person, and often we're talking about lots of people because we're working with the population distributions right now. Then we can measure them in standard deviations, which are called z-scores, and you can compare any distribution when they're transformed into z-scores. And that's the second point here. We can transform any distribution into a distribution of z-scores. And so once we do this, because the x-axis for all these distributions will be the same, they'll all be z-scores, they'll all be location scores, then you can compare these different distributions directly. And you can compare at least two of these directly. And often we're going to do comparisons of two distributions. But only possible, or I should say this is only possible once we have standardized both or more multiple distributions into, a standardized scale, in this case, z-scores. And again, the z-score only works when we know mu, population mean, and sigma. This will be very important later on once we do chapter 7, 8, 9, and 10, where sometimes we know the population mean and standard deviation. That's actually more rare than you would expect right now, but because we're working with only population data. But again, think about it. Most of the time we work with sample data, so we probably don't know the population standard deviation, and sometimes we don't even know the sample mean. But then we'll have to approximate these things. But for now, we're working with z-scores when we know the population mean, mu, and we know the population standard deviation. Okay. That way we can compare two population distributions with each other. Okay. There are other standardized distributions in real life that you may have already encountered. Now, you may remember, I'll use IQ first, since we talked about this. IQ, again, is a proportion by itself. So, remember IQ, its basic definition, it's somebody's mental age. Again, that's measured by some test somehow. Again, we're not going into whether how reliable that test is and how accurate or valid that test is, but again, working with its basic definition over its chronological age, or over somebody's chronological age. So logically, you would expect a person to quote unquote act their age or think their age. I'm doing air quotes with my hand, but anyway, what that means is, well, if somebody is 20 years old, that person is expected to think like a 20-year-old and have the mental abilities of a 20-year-old. If a person is quote-unquote smarter, that person may think like a 30-year-old if the test considers somebody with a mental age of 30 to be quote-unquote more intelligent, versus somebody who is measured to have a mental age of 10 to be less intelligent, quote-unquote. Again, the average logically here would be 100 because IQ is the ratio of mental age over chronological age multiplied by, I'm running out of space, multiplied by 100. So by itself, it's kind of already a standardized score. But once you take in the test, and you can transform IQ scores back into z-scores, and again here, 1 times 100 is 100. And then you can go, oh, well, the standard deviation here then is 15 points. And so that means, oh, okay, well, that's a ratio of 15. And that's going to be, if somebody has an IQ of, 115, well, that person is 1 standard deviation above the population average. SAT has a different population mean of 500, and a different population standard deviation of 100 points above this mean. Again, standardization and standardized distributions are used when a z-score doesn't really make sense to tell people. So if you say somebody, oh well, your IQ is 0, well, does that mean you're telling the person, oh, you have 0 intelligence, or you give somebody a serious test, or you give somebody a score of a serious test like the SAT, where it's needed for American universities, let's say, as one of the requirements, and you go, oh yeah, you scored 0 on your SAT. Okay, does that mean I got everything wrong? No, but if you're trying to say z-score, a 0 would not make sense for, at least at first impression. So instead of telling them 0, you would give back some average that makes sense to people. In the IQ, it'll be 100%. It'll be 100 because, well, originally the basic definition would be mental age divided by chronological age, which would be a ratio of somewhere close to 1, and then you multiply by 100 to make more sense for people. SAT, well, you do measure the number of correct answers at least, so again, some number above 0 that is a good approximation of the actual test would be a much more logical and an answer that makes more sense. So there are 2 steps for standardizing a distribution, and we have actually done them already. And the first step is we transform the original scores into z-scores. So then, whatever it is that you had somebody do, be it a test, IQ or SAT, first you transform the distribution of original scores, original here read as raw scores, into z-scores, so then the distribution is standardized. And then you scale these z-scores, transform them into x values, so then and you can tell people what the standard of the test is. So you can tell them, oh, the average score for this particular test, let's say the SAT, is going to be 500 instead of some odd number. Or you can say, oh, the IQ predetermined standard or average is going to be 100. And you can tell them, oh, okay, if you score 15 points above, well, then that means you are, 1 standard deviation, quote unquote, smarter. Or if you score 100 points above 500 in the SAT, well, that means you're 1, quote unquote, group above the average group. This is going to be useful for percentiles as well, the concept of standardizing distributions. So this is how the process works in pictures. So if the words don't seem clear to you, this picture should clarify it for us. So here you see the original test. The mean is some value, 57. And again, we can measure the standard deviations here. One standard deviation is 14. To transform these scores into a standardized score, then the first thing we need to do is change all these into z-scores. So the 57 becomes 0 because that's the mean. And then the standard deviations are going to be z's. And then we multiply the z-scores by some value again. In this case, instead of 57, we multiply by 50. And we change the standard deviation from 14, notice here it's 14 in the original distribution with the original scores. A standardized score here in this case gives us the opportunity, after transforming the scores into z-scores, so they're no longer original scores per se, but they're scores that we can transform into standardized scores, and you can give a new standard deviation. So instead of 14, which may be considered, less rounded, that's, 60, then a standardized distribution would have its own standardized score with its own standardized mean and its own quote-unquote standardized standard deviation. And this is only possible when we first transform the original distribution in the first row here with original scores into z-scores, and then we multiply by some predetermined mu and some predetermined standard deviation, and the person who thus the standardizing would, set these values. Again, for two purposes. One, to standardize a test to make it more consistent, and two, to make it more consistent for not only the test taker, but also for those that are reviewing the test, schools or test makers. So here's a learning check. Standardization then, in this case, remember, is first transforming the original score into z-scores, and then transforming the z-scores into a new standardized set of scores. That is specifically a new mu and a new sigma. So here's the first question as a learning check. A score of x equals 59 comes from a distribution, and these are original scores at this point, where mu is 63 and sigma is 8. So now we're going to standardize it. Give it a new mu and a new sigma. So, in the standardized distribution, the mu is now 50 and the sigma is now 10. What is the new value of this original score? You can remember the steps here. 2, step 3. Okay, so get original score and distribution. I'm going to write shorthand. Transform x into z, right? And then standardize score using z. So this is like your get x from z using new mu and sigma. Okay, so give that a try. Again, first get your original score from the distribution, from which you'll be able to transform the x value into a z-score, and then you'll be able to standardize the score using the z-score you got and getting the new x with the new mu and the new sigma from that standardized distribution. So what would that be? Well, if you know what 59 is in z-scores, that will be a great start. So your z then here is going to be x minus mu over sigma. In this case is 59 minus 63 over 8, which is negative 4 over 8, which is negative 1/2 or negative 0.5. Negative. Yeah. Okay, so once we know the z, then we've done steps 1 and 2. Now we need to standardize the score using the z-score that we got. In this case, we know where the mu is and we know the location. It's below the mean. Therefore, we expect the new x to be below 50, right? And now we need the multiplier. That's our z-score with the standard deviation of 10. So we can use the x formula, mathematically at least, but here logically we are standardizing the score using the z, by where we get an x from the z and using the new mu and new sigma in our standardized distribution. So here we got your z multiplied by sigma. So in this case it's 50, and we know it's below the mean because the z-score tells us that. And the original score tells us that also, because 59 is less than 63. And so here's 10. Well, it's pretty straightforward. 50 plus negative 5. So here is 50 minus 5, which is 45. So if you answered 45, you would be correct. Yeah. And remember to do all 3 of those steps. The steps are here, and this slide and slide 26 for 5.4 here, creating a standard distribution. And you can do that for this learning check. Make sure you practice this. Make sure you look for practice questions to do it, or make up different numbers and try it too. So here's the last bit here. Can we compute z-scores for a sample? Well, we could, but we need some things. Here, the points say, working from populations is the most common context for computing z-scores, which is why I've repeated more than once that most of the time, when you're working with z-scores, you're going to work with population distributions because you're working with parameters, namely mu, population mean, and sigma, population standard deviation. Still, you can get z-score for samples. As the points say, a z-score indicates a relative position of a score in a sample, and you can still use z-scores to indicate the distance between a score and a sample mean. So yes, you can use statistics, in this case sample values like sample mean and sample standard deviations, to get a z-score, and so it is possible, but rare or less common. Looking ahead then though, when we're able to standardize a distribution, when we're able to transform x values into z-scores, then we're given and we can work out a more consistent way of comparing distributions. In the past chapters, we're able to describe the data, we're able to do some things with the data, tell us about the expected values, that central tendency, tell us about, how far apart the scores are from each other, specifically how far apart they're from the mean, how much we should expect that. That's variability. But the next step then is for us to ask some more, quote-unquote, more important questions and more relevant questions, like, is one population different from another? Or is the sample that we're getting here different from the rest of the population? And so on. And only with a standard distribution with some standard score, starting with a z-score, only with these techniques can we do this. So conceptually, this is what it would look like. We have a population and we want to do something. Let's say it could be things like, again, I use examples like giving one group a textbook and giving another group, or everybody else doesn't have one. Or, in Alexander College, we have the Writing and Learning Center. We could compare students that, go there for help and students that don't. It could be something as outrageous as, let's say there's some memory pill or some super smart pill that makes you smarter. Does that make a difference? As ridiculous as that sounds in an academic context, the same technique we use for drugs, it could be for medical purposes, that is what happens. So like the process we use to test for vaccines in light of the time of when we're recording this, like COVID-19, the basic concept is the same here. We're trying to find out whether, something works. And we can't do everybody, so we grab a sample of the population, give them some treatment, and then we have this sample, and then we want to compare whether this sample is going to be different from everybody else. With vaccines, there may be easier ways of telling, but again, if we want to see whether this vaccine works for everybody, we can't just look at one person and go, this vaccine works for that person. That person doesn't get sick now. But again, we want to be able to say something like, this vaccine is going to work for as many people as we can. It's going to save hundreds of thousands of millions of lives. And so we want our sample to be representative. We want our technique to work, and we want our comparisons to be reliable. And so conceptually, we need a consistent way of comparing distributions. In this case, we want to compare a sample distribution with the population. Remember, these distributions are different. First, and by definition, one's a sample, much smaller. One's population, much larger. The scores are probably not going to be the same also. And so we need a way to make the comparison consistent. And Z-score is the first way that we go about this. And the reference is, as always, the mean and the standard deviation. So here's an example of this in distribution form. Here we have a population of untreated rats. Maybe they're testing something. We want to see the weight. Let's say they're given the treatment to, let's say, increase the weight, it looks like. And so here the average weight of a rat, I don't know, 400, grams. I'm half making it up here. So again, we transform that distribution into z-scores. And so yeah, the average rat would have a 0 z-score. And then we know one standard deviation, well, that's 20 grams above. Again, I'm kind of half making this up here. But the concept applies. So here, once we're able to start measuring the distribution in standard deviations, then we're able to look at any individual and say whether that particular individual, when we look at X's and go, oh yeah, that person or that rat here is very extreme. So like a score of 450, while it's just, it may be 50 grams, but in the context of the distribution, knowing that most of the rats, and we're going to learn in the next chapter, one standard deviation above the mean is, for a standard normal distribution, is 34.18%. So this area is 34.18% of the population. And two of these is going to be, well, 68.26%. So again, if we're 2 standard deviations above and below the mean, well, that's going to be close to 95%. And so a score like this, where it's above 2 standard deviations away from the mean, well, we're already looking at somebody who is very extreme. In the case that this person would belong in the quote-unquote close to 1%. So you may think of in the American world, in North America, we have this thing called the 1%. Well, this is what it's talking about, like 1% of the population owning about 80% of the wealth, as the saying goes. Well, that 1% would be somewhere here. Just this tiny area compared to everybody else. Okay? And so with the mean and with the standard deviation, when we're able to look at it in a distribution, in particular a standard or standardized distribution where we measure things in standard deviation, we're able to say, well, how far some individual is away from the mean and how likely in terms of probability, or how much of the population is that person, in. If somebody's in average, well, that person's in the majority of the population, whereas somebody with an extreme score would be in the minority. And this is the concept that we're going to use to compare distributions to. If a distribution, let's say the sample here has, the majority of that sample being in that extreme value in the population, then we might say, yeah, that sample, something's happened to them. It made the rats, in this case, going back to our original topic, the rats heavier by a lot. We no longer see rats with the average weight, but they're really some extreme weight now. And that's not the new normal. So you might think of quote-unquote the new normal, how COVID-19 is changing things, making things different from before, from the way we normally do things, that most people do things. So that's how we make comparisons. And in the future chapters, that's what we're going to look for with numbers and means and standard deviations and distributions, starting with z-scores. So here's the last bit of learning check then before we finish for the day. Here's question 6. The question reads, last week Andy had exams in chemistry and Spanish. Again, this is a case now where we can actually compare tests. On the chemistry exam, the mean was 30 with a standard deviation of 5, and Andy had a score of 45. On the Spanish exam, the mean was 60 with a standard deviation of 6, and Andy had a score of 65. Here, by comparing distributions, for which class do you think Andy can expect a better grade? Again, you have everything you need. You have the raw scores of both tests. You have the means and standard deviations for both tests as well. So take a moment and see if you can figure it out. Again, you'll want z-scores for this, so you want to find out where Andy is in relation to the class for both of these tests. So I'm going to label the z-score for chemistry as ZC and the z-score for Spanish as ZS. Again, I can use the same subscript here for the values that we have, be it x, mu, and sigma. Okay, mu and sigma and mu, x, mu, and sigma, I should say. Okay, let's plug the values in. Okay, I'm getting straight to the math at this point because I explained the logic multiple times. So 45 for your chemistry test. Yeah, okay, 30 here divided by 5. Cool. And here you got 65. If you already kind of know the answer, great. Again, most of these learning check questions you can kind of tell by looking if you already understand and apply the concept. Okay, let's check the numbers here. For Spanish exams, x is 65, mu is 60, and sigma is 6. Okay, so let's check our locations. Well, he scored above average for both of them. Now we need to see how far Andy scored above the average. Okay, so that's 15 over 5. Ooh, z-score 3. Okay. Okay, and here for Spanish, we have 5 over 6. Okay. Well, one z-score is definitely larger than the other. In fact, way larger. Z-score 3, if I did my calculation correctly. Let's check one more time. Yeah, 45 minus 30. That's huge. Probably got an A plus in that class with z-score 3 like that. So, yeah, which one's better? Well, if you said chemistry, you'll be right. Yeah, a z-score 3, that's really extreme. That's like 99% of the people would have a score below that. Again, looking at the z-score in relation to a standard normal distribution. And again, the other one with the z-score for the other guy is 5 over 6, so that's less than 1. So Andy would kind of have done average there. So yeah, one score is way above the average. Therefore, that score for the chemistry is much better. True, false here for question 7, 2 parts. Here we go. So let me fix that while I read the question out loud for you. A and B. Change that to this, I guess. Okay, cool. So, A, transforming an entire distribution of scores into z-scores will not change the shape of the distribution. True or false? This is a concept definition question. And B, if a sample of 10, and the sample size here is n is 10, scores is transformed into z-scores, there will be 5 positive z-scores and 5 negative z-scores. True or false? Second one, you might need to think about this a little bit. Notice the assumption it's making here when, in the second part of that sentence, there will be 5 positive z-scores and 5 negative z-scores. Take a moment and think about that. So, the last few questions here. A, B. Okay, here, this would be your bullet point. Oh well. So, for A here, transforming an entire distribution of scores does not change the shape. That's true. We're, in one sense, merely relabeling them. But we're doing a transformation of each score, but we don't change its location. We don't move scores. We don't add or subtract anything. We multiply. We find the deviation score and divide it by the number of standard deviations. That's it. or divided by the standard deviations to figure out the number of standard deviations. That's what we're doing. So A is true. For B here, there, I've fixed it, I think. There you go, fixed. So for B, if a sample size 10 has been transformed into z-scores, does the assumption work that there will be 5 positive z's and 5 negative z's? No. You may be thinking, oh yeah, for the distributions we're looking at is symmetrical, so that kind of makes sense. Yeah, it would have if the even number of scores on both sides, but all we do when we change the scores from x's into z's is we transform the scores only. We do not change the location of the scores. If the distribution itself was not symmetrical, it will stay that way. If the distribution was symmetrical, it'll stay symmetrical. We do not change the shape of the distribution at all. Here's an example. Well, this distribution is not symmetrical, but when we change the scores into z-scores, notice the blocks don't move, but the numbers change. That's it. Everything else stays the same. The y-axis is the same. The blocks are the same. The standard deviation, or the distance between the scores are between that and the mean. Those are the same. But we measure, instead of x's, we measure in standard deviations. So that's it. So the mean here is some x value, free. The mean here is 0. And then all of these are measuring standard deviations. So there you go. So that's it. That's our one chapter where we went through the whole thing in one go. This is probably going to be over an hour. But we have covered 5 outcomes. In one sense, this is one of the easier chapters because we only cover one formula. And I'll show you where the formula is in the formula sheet. You probably didn't need the formula sheet for this if you went through the whole video in length. If you are able to describe the definition of a z-score, you probably won't forget the formula. But the formula sheet is there nonetheless. So having completed this video, having completed this set of, slides and instructions and guides, you have achieved the following outcomes. 1, you're able to describe the z-score as a location in distribution and say what the definition of a z-score is. You'll be able to transform x values into z-scores. You'll be able to change the z-scores into x values, which you'll be able to do 2 things. 1, describe the effects of standardizing a distribution, where you don't change the shape of the distribution, but you relabel the scores from x's into z's. And being able to change x's into z's and z's back into x, so to speak. Then you're able to standardize distribution and give a raw score of an x value a standardized score using a z-score to figure out its location first. So that's it. That's chapter 5. That's z-scores. That's standardizing a distribution in preparation for the next chapter. That is probability, as we figure out how much of the population is going to be place for a particular score, either above or below it. And so, yeah, stay tuned for that. Again, as always, use your practice questions in the textbook and in the web tutorials to help you. There's no substitute to practicing here, especially with concepts and techniques. You can also review the video and do the practices there. And if you're still stuck, you can ask me questions about stuff as well via email. So the last thing is the formula sheet. And so if you're taking this class at Alexander College, you can find the formula sheet in the modules, in the summary of statistics formulas, page 1, right here. And if you click this, you'll get the formula sheet itself. And it isn't loading right now. You can download the sheet here like this. Download the sheet, open it up, and I'm going to enlarge it for you. So we've done the first 4 things so far: mean, sum of squares, variance, and standard deviation. So we move down a little bit. And we're mainly working with the first one for now, but you can also take into consideration the second one. But I will draw the ones you're going to need. This is the one that is derived from the definition of a z-score. The number of standard deviations is a score is away from the mean, or the distance a score is from the mean measured in standard deviations. Here, the z-score for locating a sample mean, we use the standard error. This is going to be used for a later chapter where we talk about approximating a population distribution using an infinite number of sample distributions, which is called a sampling distribution. And we're going to talk more about this in chapter 7 in this course. So that's it, guys. So that's our chapter 5. We've covered the slide, we covered the learning outcomes, and we showed you where the formula is that you can use for this chapter. Again, make sure you practice your questions. Make sure you review by self-testing and practicing. Ask questions when needed after doing those things. And there's no substitute for practice. Get ready for chapter 6, probability, and we'll see you in the next one.